I'm Lee McCuller. I just recently joined the LIGO collaboration at this exciting time. Actually a very recent graduate of the University of Chicago. I actually worked for McCuller, who's down in the front. I now work at MIT in the LIGO lab doing R&D research for future upgrades of the LIGO instrument. So with this talk, I'm covering for Ben Farr. He's at the April physics meeting. And so I'm going to cover, and since I do instrumentation, I'm actually going to cover the LIGO instrument, the interferometer and the associated equipment that actually made the detection, became sensitive enough to make this amazing detection. And what I'm going to start off with is I have materials from the collaboration. I'm talking on behalf of the collaboration since I joined earlier. This is all the work of a very large group of people, and it all occurred before I joined. So I have to give due credit to a very excellent collaboration that I'm lucky to have joined. And I'm going to start with a video that was prepared. You may have seen this from...
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our sun, were locked in orbit and spiraling in towards each other. The only visible traces of the spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in the system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself, and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
Things about this video. One thing, you saw this waveform and this chirp that happened multiple times as the waveform was going past. The chirp, this multiple times that's showing in the video, that's not how the event actually occurred. It only occurred exactly once. The fact that it sounds a bit like a heartbeat repeating is just so that you can hear it and get a chance to hear it multiple times. There was only one collision in one waveform that we heard one time. Just so that that's apparent. And what I'll be covering is the part where they zoomed in on the instrument and how it became as sensitive as it is. I'd like to go over how the instrument works and how that happens, and I'll just give a brief overview. I'll go into the gravitational waves. This is something that Ben Farr and the rest of the series, I think, will go in much better. And he does more of the gravity and the data analysis side, so he's actually much better at covering that side of it. As for the instrument, I'll start with an overview on how these optical instruments work, the Michelson interferometer. I'd like to divert a little bit into just measurement and how, what are the limits of measurement, and how is this instrument so unique in its ability to be sensitive? Yes, sir.
Does a spinning black hole cause, a single spinning black hole cause gravity waves?
No, a single black hole will not cause waves. It has to be in a binary system. It has to be two different masses, and there has to be motion of the masses. A single mass is so symmetric that it does not create any wave emission. And then I'll get into the specifics of the LIGO detector and what makes it so sensitive. And then finally, a few possibilities for the future, including a little bit of what I do now. And so here are the instruments. You saw a picture in the video, but here's the 4-kilometer interferometer in Louisiana, in Livingston, Louisiana. I've actually just recently been to this site and been in, touched the instrument. It's really quite cool, and I'll have pictures of what it looks like inside. Here's the one in Hanford, Washington. This is in sort of desert flats, and so it's a great area, not too populated. These two instruments are quite distant apart. The distance is very good for trying to localize where the signal is. So it's almost like you have two ears, and it's hard to find out where sound is coming from, except that you can somewhat triangulate based off of the time delay between when you saw a signal in one and the other instrument, and determine where on the sky the signal was coming from. And that requires you to have two instruments that are located some distance apart. And this was as far as, you would like them to be even further apart in the world, but this is about as far as we could get good sites for in the US. But in the future, other instruments will be coming online. Currently, only the Hanford and Livingston sites are operational. Italy has what's called an Ergo Machine, and it is a 3-kilometer machine, not of the LIGO design, that will become nearly as sensitive and will be a huge boon in the ability to locate these sources. The Geo 600 machine is 600 meters, and it is a research instrument for developing technologies that will work well at the other sites. And then soon, or in the next several years, India is trying to acquire and build a third LIGO version instrument. And then finally, Japan is running a very sophisticated instrument, or they're starting to develop a very sophisticated instrument that uses some future technologies. They'll be very impressive in a number of years when it is operational. And so how do these Michelson interferometers work? You saw briefly in the video this little cartoon of how the waves travel through them. And I'll actually show that again just so that you catch all the features of it. But the basic idea is that you start with a laser. It sends light towards this beam splitter, which actually creates two separate beams of light that, as it travels down either arm, is coherent. The waveform is at the same phase because it started from this same point on the beam splitter. Travels down both arms and it comes back and it recombines. And at this recombination point, the two phases of the return light are compared. And you get constructive or destructive interference here. And it redirects light either out of this port, where you would measure it out of power meter, or out of this other backwards port that's heading back towards the laser. And you could, in principle, measure it there. I'll get into reasons why we don't do that for LIGO later on. But the basic idea is it's recombined. You can then convert, and when it recombines, that phase measurement that it compares essentially measures length, because the length is what determines the phasing of the light that gets recombined here. And if you work through all of the math and you determine how much power do you see on this meter, it is there's just a function of it, and it's a sine squared. It's not a linear function. But if you use control systems and you hold the interferometer at a constant length, it will sit at a constant power, and what you watch are for deviations in the light output. And when you see a deviation in the light output, you know that the lengths change. And so you can convert that deviation in the light output in this function of the two arm lengths back into what the arm lengths must have deviated by in order to reconstruct the arm length changes. And of course, the gravitational wave acts as a changing length of the arms through the stretching of space-time, and that is converted into a gravitational wave signal. And so, but what you see in most diagrams is you just see this, the beams folded back, where the incoming and outgoing beams are actually on top of each other. So that little beam that was up here is actually going back to the laser, and you can divert it off and you can measure it. It's just, for practical reasons, this is the better way to run them, and I'll get into why those practical reasons exist.
So
Yes.
you're using the word power meter there.
Yes.
So you're not looking at what we would think of as classical interference fringes. You're looking at something else. How do you define power in that?
Oh, so the power is actually the light, like the number of watts of light that you're seeing. So you actually do see the fringes. If you were to move these arms by 1 micron or 1064 nanometers, the wavelength of the light, you would actually see the sine wave, and those are the fringing. You would see the fringing. And so I think we are actually doing as you're thinking, calling it a power meter simply because we're measuring the number of, how many watts of light. So this laser pointer is outputting a milliwatt or so, and we would measure that in our power meter just the same. And in practice, this power meter is a photodiode. I just didn't use the technical photodiode word. And we actually measure this as a function of time, so we get a constant readout of the power. And then we say deviations in that constant readout correspond to deviations in this length. And so that's how we know that the arm length has changed. And I'll go, let's see if I can click on this, back through this video of the light traveling down the arms, and you can see this fringing or this interference. This is a waveform from the gravity wave, the cartoon of it beaming through. This is the sine wave coming from the laser. It is split by the beam splitter, and it is coherent in the two arms. It goes through the path length, across path length, and it's folded back, reflected by the arms. And here, when it hits the beam splitter, it is compared again. And as the arms go back and forth, if you look at the output here, this is currently destructive interference. And now, as the arm lengths change, you see the fringing occur, and you see this sine wave function that I just depicted. And so we actually sit it somewhere where it's not going through a full fringe. It's just sort of sitting at one particular power, and we look at small deviations on that power, and that's what we can convert into length. Close this. And this is, so that laser system and the beam splitter is all enclosed in a vacuum system, because even the air of the atmosphere actually causes fluctuations in our light power that would look like path length. But we don't want those fluctuations from just air, so we have to put it in this giant vacuum system. Just to give a sense of how large this is human scale. This is evacuated to an extremely low pressure, and it has to do this. It has to have a perfectly sealed steel structure that is 4 kilometers long. It was a huge development and investment to do this, and this is even the early versions of LIGO had this very same system, and it's all been upgraded within this vacuum chamber in order to become advanced LIGO, the one that is so sensitive that it made this detection. And so how does this work to detect gravitational waves? Well, the gravitational waves, if they're passing into the page, stretch and squeeze space-time alternately in the two arms. So as one passes through, it will squeeze one arm as it stretches another. And that causes a plus delta L and a minus delta L. So if you're at some constant readout of light, you see this deviation, which is 2 times the stretching and squeezing in any single arm. And this is the deviation in the light that you can convert back into. You can then reconstruct what is delta L from this. And this is put in terms, wrote it as delta L as a length, but the gravitational wave is in units of strain. What strain is that is a relative change. So over the 4 kilometer baseline, we say 4 kilometers times h creates the delta L. So all of the plots are put into units of this h, this relative change. This is why having such a big instrument is so important, because you get a larger baseline to multiply this h by, and that lets you have a larger thing to measure. And that's why you need such a large instrument. And so how does this show up as the waveforms that we see? These colliding black holes create this changing waveform that is at the beginning oscillating as the two objects are far apart, and it's sort of a constant period. As they get closer together, they radiate more. meaning that the rate that they fall inwards because they're radiating their energy, and so they have to get closer together in order to, because they lost energy and their orbits are decaying, so they get faster as they get close together. So this waveform is accelerating, and then suddenly this sort of singular event happens where they actually do this merger. And this waveform does this, and this final chirp. This is where all of the huge energy output occurs, where it blasts large enough that you can see it throughout the universe. In fact, for this binary black hole merger that we saw in September, it was 1 gigaparsec away, or 3 billion light years away. And what this looks like, this waveform, actually you can sort of visualize as this changing tube of this stretching and squeezing signal. And this tube is traveling through space, and it would go into the page, into the plane of our interferometer, stretching and squeezing as it flies through, and this causes the waveform that we see. And in our system, we saw it in the 2 separate detectors, so it wasn't something that we saw by happenstance once. We actually did see it twice, and all of the statistics were done. Ben can get into all of that about how what is the likelihood of seeing the same signal in both detectors that didn't come from some common source of astrophysical origin. And it was extremely unlikely that any other thing other than an astrophysical source could have caused that same waveform, especially a waveform that happened to look exactly like a binary black hole merger as predicted by theory. And this is a plot from one of the papers. I'm not going to go into full detail. You should get Ben to do that for you, because he's really good at that. But for this talk, I'd like to just cover the instrument. But just to give a sense of scale, this thing arrived on Earth, this 1 gigaparsec away, 3 billion light years away, 3 billion years into the past, and which is a large fraction of the age of the universe, how old this system was. And just since we used a month of data and we saw one event, you can sort of predict how often these kinds of things are occurring. And there's something like 200 to 400 of these mergers each year in this kind of gigaparsec volume. And this is from one of the astrophysical papers. And so when we turn back on later this year and we run for 5 months, you might hope that we see 5 events. And that's just going off of the kind of rate that you would expect. But what's amazing about this is that it came from so far away. It was this huge event. And by the time it reached Earth over this 4-kilometer baseline, it only moved the test masses, the end mirrors that we're watching, 1,000th the diameter of a proton. And so we had to be an extremely sensitive device. Yes?
Don't those mirrors have to be calibrated to that small distance?
So
each compared to the other, and how in the world do you do that?
Well, what's amazing about this, since we're not just looking at the DC, like the steady state length of the mirrors, we're watching for this waveform, this changing length, or this changing baseline. And that's what allows us to not worry too much about their exact distance. Their exact distance is like, what is their distance that is steady? And since we're only looking for the deviation from that steadiness, we don't have to worry about that exact distance. It's because it's at some sine wave, like the sine wave that we're looking for, or the waveform that we're looking for, can be sitting on some long distance, but since we're only looking for the deviation, we can sort of ignore the fact that it's offset from 0, from an exact distance. I hope that answers your question. Yes?
I assume that both of the detectors, the one in Louisiana and at Washington, are at ground base, they're not on a satellite?
Those are both on the ground, yes.
Okay. So how do you account for the unavoidable perturbations due to the mass between, let's say, space and the ground?
The mass between space and the
Well, would that perturb it? You're only talking
Oh, right, so like the volume of air above the...
Or anything else than that.
Yes, and in fact, the air above the detectors, just the moving mass, does create gravitational wave signals that the rest of the instruments cannot somehow avoid or ignore. You can try and predict what they are from having external sensors, but the fundamental thing about those masses is that they are not shared between the two instruments. So the same air volume above each one isn't shared, so having a common waveform would not occur by having this mass.
even so, there might be perturbations that would be an artifact, would they not?
Yes, well, so, and that causes lower frequency rumbling and it's called Newtonian noise. And I'll get into that later on. But you're on the right track.
All right.
Yes.
So the light meter that's measuring the intensity of light that's output,
Yes.
is measuring it as a function of time, and there would also be a corresponding distortion in the function of time with the space-time wave that's affecting the length. That's somewhat confusing to me, how you would parse that.
Two separate effects that are being affected. Right, and so the reason, you're right at some level, it would affect, the gravitational wave sort of affects everything, but the reason why it's not hard to, why it doesn't confuse the instrument is that because the optical system as set up is so much more sensitive than the other ways that the gravitational wave would affect that light. There's billions of times more sensitivity of the gravitational wave affecting the light in the instrument to the gravitational wave affecting the light like on its way to the detector. And so there's not really, it's subtracting 1 from a billion. So it doesn't really affect the result in any case. And yeah, if that's still confusing, I can once I have diagrams up, maybe I can point out what I mean.
Thank you.
So I'm going to divert a little bit on just oh, yes.
If I heard right, you said the sensitivity of the instrument is 1,000th of a proton diameter, and your detection was 1,000th of a proton diameter. So you're really doing something right at the edge of your detection abilities?
For this event, so the trick is the fact that we're measuring over time. So in a single second, if you just measure for a single second, then you only get a sensitivity at this of the 1,000th of a diameter of a proton. But because there's a waveform, it depends on how the fact that you're doing this over time and you're doing statistics, you actually, depending on the waveform shape, you can actually reach a little bit below. This comes down to the way the data analysis fundamentally works. And I'm afraid that at the moment, why don't I come back to that later on in terms of the waveform. You're actually onto something in terms of how the sensitivity works. But once I show you spectra, I can maybe explain that a little bit better. Yes?
Since it's been determined that dark energy is accelerating the expansion of the universe, did you have to take that into account in your calculations?
I'm less of an astronomer, so I can't give an exact answer to this, but my understanding of it is that for these events that are so far away, like this 1 gigaparsec away, when you actually try and calibrate out the distance that it is versus the time it took to get here, you actually do have to use coordinates that are adjusted for those effects. And actually, if I relay that question at the end of the talk to Craig Hogan here, he can probably answer that way better than I can. But that's my understanding, is that you do account for it in kind of the way you state the coordinates of its location in the universe. Oh, yes?
Your detection system, what is the time, what is the time it takes to record a single point? In other words, how rapidly are you able to record the changes?
So the actual readout speed is 32 kilohertz. So it's actually much faster than the waveform itself, by a factor of 100. Okay. And so you have to do all the data analysis to make sure that it's fast enough, that there aren't artifacts due to that, aliasing and that sort of thing. Yeah, I can get into more if you'd like. But yeah, it's significantly faster than the waveforms that we're expecting this.
Can I suggest that you take questions after the lecture so you can...
Oh, so that I can keep rolling on. Yeah, I'll try to do that. Okay, so I'll divert a little bit onto what is the nature of measurement and why is this device so particularly sensitive. And I'll go into an example of a little bit of light and sound, and in this case, sound. So let's say that you have someone far away from you and you want to hear what they're saying, in this case, spying. So what do? You make a device that turns up the volume so that you can hear it better. But you can't just keep doing that. You can't hear arbitrarily well. So what are the limits of doing that kind of thing, of just turning up the volume, having some kind of detector? Well, one of the, you just turn up these knobs, the detector. You can actually turn up knobs depending on various factors of what you're trying to look for, how far to move it. So one of the things are just background. So if you're trying to listen in on someone, there are birds chirping and cars. if you turn up the volume, you're just going to hear those better as well. So there's a limit if you can't get around and you can't isolate yourself from the backgrounds of what you're trying to listen to, then that's a problem. And later on in the talk, that's a huge piece of the technology that goes into LIGO, is getting past backgrounds of just seismic noise, the ground rumbling, cars driving by, because those move the Earth far more than a proton diameter. So how do we do that? And I'll get into the seismic isolation systems a little bit and show some pictures. The next thing are sensor noise. So when you have a detector like our photodiodes, you have to engineer them very well so that just the electrons flying around the electronics don't crackle and hiss. And in fact, what you're doing when you're trying to turn up the volume is you're switching between the sensitivity limits of your ear and the sensitivity limits of the device that you're using to amplify it. But ultimately, that device might have a limit. If it's engineered well, then you can generally overcome that, and that's not a problem either. And then, so let's say you could isolate the backgrounds. You could engineer your amplifier really well so that that's not a limit. But ultimately, you hit a fundamental noise. For sound, it would be the fact that sound waves are traveling in air. Air is made up of atoms and molecules bouncing around at some temperature, and those are actually running into your microphone. So if you turned up the volume enough, all you would hear are individual atoms punching your microphone. And so there's a limit to that. And for our optical instrument, we're hitting that limit as well, but not with atoms carried on air. It's the fact that we are using light. We're using photons traveling down these two paths. Those photons, yes, they are waves, they have interference, but they are also particles. And those individual photon particles, despite the fact there are very many of them, 1 watt has 10 to the 19 at the wavelength that we are using. When we measure them on our photodiode, we are limited in sensitivity to individual photons punching our photodiode. Every single one of those photons has 1 over 10 to the 19 watts worth of power, and we see the fluctuating power because they're just raining on us. We're hearing the crackle, like the hiss of rain of these photons on our diode. That is the fundamental limit of our instrument. And of course, in some sense, it's not too fundamental. Just turn up the power and you can listen better. But then you hit engineering constraints. And I'll go into where we make those trade-offs between photon fundamental noise and that. And the way that you think of how sensitive are we, well, every single individual photon particle can essentially measure its wavelength over 2 pi worth of resolution. And when you have 10 to the 19 of them, you get to, this is like a standard statistical improvement, like polling for politics. When you have more people that you poll, you can make a better measurement. We poll 10 to the 19. We start with 10 to the minus 6 meters. And so that, the 10 to the 19, take the square root. That's 10 to the 10. So we get about, with 1 watt of light, you can get a sensitivity of about 10 to the minus 16 meters. And to give you an example, that's about 10 times the diameter of a proton. And so in order to get 1,000 times better than that, you need a lot more light, and that's what LIGO does. And this is actually our laser. It's a 200-watt laser that we use. But we don't just have 200 watts. We use tricks to make it even larger than that. And it's just this big optical system. When you're working on it, because it's so high powered, you have to be in this garb. Sorry that it's weirdly rotated. But basically, any dust on here, dust on mirrors, causes the beam to scatter and refract. And when you have so much light, any amount of light that goes somewhere you don't intend will burn things, will cause issues with plastic. It'll basically ruin it. So you have to be extremely clean here. And so now with that, with what is sort of the fundamental limit based off of the photons, I'll start going into what is the noise curve, what is the sensitivity. And what's interesting about LIGO is that it's, and this is the fundamentally confusing thing about how LIGO sensitivity works, is that it is frequency dependent. This waveform, as it travels, actually is changing in frequency. At early times, it's sort of a lower frequency, and then it chirps upward, and it gets higher frequency, and then suddenly it disappears. And what that looks like is it's sort of sitting here, and it kind of rolls down here. So as it chirps higher in frequency, its amplitude goes down. And the reason its amplitude goes down is that when it's at higher frequency, it's doing it for less time. And so I'll try and explain what this bucket shape is all about in terms of the frequency. To give an example, I'll use a little bit of optics. Ooh, that's really hard to see on this projector. Okay, well, so there should be 2 little targets here. Yeah, I don't know what's wrong with my image here. Sorry. But you can see the targets in this noise. They're actually roughly about the same visibility. But you notice that you can see this one better than this one in much sense. Maybe, you know, I don't know if you'd make that call, but this one is a little sharper. It's crisper. It has these sharp edges. And in a spectral sense, this background image has some noise curve, and it's mostly low frequency. It's mostly large features, these blotches, and then maybe some smaller features. So I kind of cartooned it out as going down. This blurry image, which was supposed to also show here, is this red one. And it's harder to see because it is kind of buried underneath the general noise of this background. But the crisper one, this target, has sort of the same amount of power, but it's spread up, and it actually reaches above this noise floor here. So you can see it. To contrast, here's another image where the image background has a lot more high-frequency features. And suddenly you can see the low-frequency guy more, and the high-frequency guy, which is actually here but barely visible, you can't see because it's drowned out by the other sharp, high-frequency features of the background image. And so suddenly you can see it here. And we're doing the same thing, except in a kind of an auditory dimension, not 2D like this image, but in this time series of the power readout that we use. And this is the hissing of these individual photons, this rain noise that you hear of individual photons hitting our detector. And I'll get into why our optical layout is a little more complicated than the one I originally showed you. But what you're ultimately seeing in this hiss of the individual photons causes the bottom of this bucket. It causes a white noise floor, which is static sounding, which is sort of what you heard on this slide, is staticky. And that is the individual photons. Now, it curls up here, and that's for a particular reason having to do with these arm cavities. I'll try and explain that in a few slides. And then down here, which I'll have a sound, I think, in a couple of slides. Let's see, is it this one? No. So this is just showing the white noise hiss. And this is for the single interferometer. And what I'm breaking this down is that this previous slide, which has been this again, this previous slide has just the sensitivity and strain, and it's in these weird units, 1 per root hertz. And I'm going to break that down in this slide here, where this is sort of decomposed or budgeted out as a noise variance, a variation that you're measuring as a function of frequency, and in units of a density over that frequency. This is the variation in the watts that you're reading. And that's limited by the watt of every individual photon. And this is just a flat function. It's white noise. And so for a single Michelson, let's say 40 meters, a shorter instrument, you get this, the photons that you're reading in this power meter watts per strain. This is a sensitivity. As you see a deviation in your strain and your H, your delta L over L, this is the conversion into a deviation of watts. And this is a flat function. Not too much interesting with these functions, but the way you get the previous plot is you divide this by this. And that gives you an H per root hertz. It gives you a spectral density, and lower is better. So the lower your sensitivity is, the better you're able to resolve things over it. But so what's the easiest way to improve this machine, given this kind of breakdown? I know this is getting a little technical, but the best way to improve it is simply make it longer. And the reason is that if you make the baseline longer, you get to divide more here. That shows up, you do the math, and this L kind of shows up on the numerator. So it raises the sensitivity. So a smaller waveform will give you a larger deviation in the power that you're reading out, which is great because when you take this and you divide it by this, it lowers the sensitivity plot. So you're more sensitive. And that's the first easiest trick that LIGO did, was just make a big, long instrument to gain that huge initial boost of sensitivity. The next thing it does is, as I mentioned, having more photons is better. It gives you a larger power deviation. It increases your noise a little bit too, but you overall win when you have more photons. And that's the square root improvement. So the first thing that you do is you do this trick. And this is why the alignment of the mirrors isn't the original misaligned. We actually keep them folded on top of each other. Is that the light that would otherwise be going back to the laser, we put a mirror here, and it sets up this optical resonance, this cavity, between this mirror and the arm system. What this does is it allows us that if we match the laser to this cavity, and this is like, let me think of a good example here. If you hit like the resonance of a musical instrument, like you can ring a bell just by like if you sing the right note, you can ring up a glass of water or some cavity with the same resonance as the tone that you're generating. That's what we're doing with the laser. It amplifies the light in the cavity. So even though we only have a 200-watt laser, we can get much more power in our optical system. And that suddenly makes your sensitivity go up, makes your noise go up a little bit, but you overall win. That's great. However, you hit a limit. As you keep increasing the power, a lot of power has to go through this optical substrate. This is glass. Glass is a little lossy, and you lose some of the light, and it heats up the glass. And then it starts focusing. It starts doing bad things, essentially, to your ability to control the beams. So we use it off. And this is going back, so you divide these two. You divide these two plots, and that keeps dropping this down. And one of the things for the initial LIGO to advanced LIGO, that was one of the improvements. We have more power now, and it takes this bottom from the initial LIGO and it drops it. And we do other tricks to make it wider, make a wider floor and all of that. So what do we do in order to not have too much power going through this substrate here? Well, we make a trade-off in the amount of power in this section and the amount of power in the arm. So we do this optical cavity trick a second time, where we do it individually in each arm. So one thing that you could think is that more arm length is good. So what if you were to take the laser and you were to misalign the arms and do some tricks where you got it to just bounce back and forth and then go back and then go. And so you sort of fold your arms over and over and over again. So you effectively get more length for free. Well, for practical reasons, that is actually really hard. But you can get essentially the same thing when you do this cavity. That's what these cavities do when they are installed on the arms, is that they give you more power, more sensitivity. It will amplify your signal by essentially folding the arm on itself without having the practical issues of this kind of bouncing technique. However, there is one trade-off. So that's why I show in this plot, you get this increased sensitivity. Your photons per strain, or the power deviation you're measuring as the waveform goes through, has increased, so you've won. However, the cavity itself has a resonance. And so it has some bandwidth associated to it, or some limit, frequency limit over which it can resolve. So what this means is that if your gravitational waves are too high a frequency, you actually stop gaining the benefit of the folding because the arm cavity resonance won't enhance at whatever that high frequency is. And this is this roll down of the sensitivity. Okay? And so when you take the white noise, you divide by the sensitivity, that is exactly what causes this. Ooh, I'm having difficulty. That is exactly what causes the roll up. Sorry. I'm having trouble here. Okay, that is exactly what causes this roll up here, is when you do that division with the rolled down sensitivity of the arm cavities, it causes your sensitivity floor to roll up. And so the final trick, and I can't go too much into detail on this one, is this final, what's called the signal recycling cavity. It's yet another cavity, but what it does is, and you notice that I changed like the width of these lines on the other times to signify that you amplified the power. The signal cavity is actually, it wasn't in the original initial LIGO because it's kind of a tricky thing to do. It makes running the instrument a lot harder, I'll tell you that. But it doesn't amplify any of the optical fields which are converted into, that have phasing delay lines. This one does something interesting. It creates a resonant cavity, not for the light power that you're trying to convert into signal as the gravitational wave travels. What it does is that after that signal is generated on the light wave that is compared here, this cavity, this special signal recycling cavity, just amplifies the signal that is generated. And it kind of sucks the signal out of the rest of the instrument. Which is kind of, that's why it wasn't in the original one. It's a tricky thing to do, and it's kind of hard to explain. But what it does is when we turn it on, it actually removes a lot of the disadvantage that you have from having these arm cavities, which is quite a neat thing to do. There's actually other ways to run the signal recycling cavity, and you can actually change this function. But for the general purpose instrument for making lots of good gravitational wave detections, we kind of have it at this tuning where we just sort of win a little bit everywhere. But if suddenly there were way more sources somewhere with very particular gravitational waves, we might actually be able to optimize for them using this device. So now I'll get into some of the other background noise sources. I've kind of explained how we use the instrument and design the instrument to overcome the fundamental noise. And now I'll get into what we're doing in order to get around the other noises in the instrument. And so here is what you just heard was kind of a thermal noise. This actually wasn't in my example with sound, although there's probably other analogs. And basically this thermal noise is that all of your mirrors are at some room temperature. And so they have molecules jiggling around, just like the molecules in the air. And that causes a noise because just that jiggling actually does imprint a little bit on your light. And it has a certain frequency spectrum. And in our case, which molecules are doing the most jiggling that affects us? It's not actually the molecules inside of the mirrors. It's the molecules on the coatings of the mirrors that make them highly reflective. And it just so happens that the way the coatings are deposited forms these little fingers of atoms, and those like to jiggle a particularly large amount. And so that causes this kind of interesting spectrum. And there's some research to make that better. And I can't get too much in detail on how all that works, but that's the general idea, is that individual molecules averaged over the whole surface are kind of jiggling the location of the mirror surface. The next one, which is even larger than that, but we actually made it smaller with a lot of development, is seismic noise. This is the rumble of the Earth. And actually a little bit the rumble of the air currents above it, as one of the questions. And you're hearing this very low frequency rumble. This is actually converted up. If it were really just 10 hertz, like it is in our instrument, you couldn't really hear it. The ear doesn't have any sensitivity there. So we converted it up to I think that's 40-ish hertz or so. And here I'll get into what we did to isolate that, because the Earth is moving a lot compared to the diameter of a proton. And it has a particular spectrum. So how do you go from the Earth moving, which it's moving kind of a micron every second, large rumble, how do you get it down to such a tiny, this is in strain units, but this would be 10 to the minus 19 meters. So it's going from 10 to the minus 6 to 10 to the minus 19. How do you do that? And what we do is we use, if I can move on, and this is just another breakdown actually of this spectrum. This is the real data where you can see there's other things going on in there. And I can talk a little bit about those in the future. And here's seismic. It all has more shape than I've explained. And there's actually currently for this release, there's a little bit that we haven't fully explored yet. There's more than we were budgeting. And that's to be expected because we're still improving the instrument. So I'll go, and it's probably seismic, by the way, or somehow at the root cause of seismic that's somehow shorting out the rest of the instrument. I'll get into that in a moment. But here's the vacuum system again, just to give you a sense of scale of how big these things are. So how do we get rid of seismic isolation? Well, we have this really quite fantastic system where the ground is shaking. We have an active pre-isolator that sort of measures the shaking up here using inertial sensors, and it tries to neutralize it as best it can. And this is actually hydraulic. It can move big motions, but only very slowly. And then we do it again, and we have the active internal isolator. And this does the same thing. And it goes on. I'll show some pictures that maybe are a little less abstract in a moment. And these also kind of measure how much am I rocking around. And I'm going to try and zero it out using some actually by physically moving this thing relative to the Earth, which really is keeping this still and letting the Earth move underneath it. So you do that 3 times. And then, and that's all active, so that actually gets limited by electronics and how well you can sense how much you are staying still versus the Earth. And then you have this long suspension that is all passive, where this can still be moving a little bit, but then as that's rocking, it can't get down to this optic as well because there's a string And actually, I could demonstrate this, where if I move this fast, you notice my arm is moving much more than the remote control, which is hanging off of it. It's the same principle, actually. And here you can see sort of a layout of this thing mechanically, and you can see the suspension. All of these wires for the suspension are actually hanging inside of here. And this is what it really looks like. And the mirrors are 40 kilograms. They're like wedding cake size. It's really quite amazing. And eventually they're hoping that it might be possible to make them even larger. And so this is this hanging pendulum that is at the end of all of this. And you see there's actually 4 stages. It's 4 separate pendulums, which happens to work better than one once you get to higher frequencies. And I'll explain that hopefully a little bit better, especially if you have a question. And there's lots of little pieces to this to make it so good. It has very thin wires, so that the wires aren't actually, the shearing of the wires doesn't short out their ability to rock as pendulum. And the most amazing thing about this is that the wires on the lowest 2 masses, just glass doesn't have this thermal noise issue as much as metal does. So the second to last mass is also glass. And the connection between it and the bottom mass is actually glass. It's not metal wires. They actually took glass, they melted it, and then they pulled it in these tiny, very fragile strings. Less fragile than you think, but this forms, and they have these little ears where it's hanging from. And this is actually like a huge, the initial LIGO didn't have this. This was a huge benefit to the ability to isolate seismically while not actually adding noise, because these wires add their own thermal noise. Like they're at room temperature, they're shaking around a little bit like violin strings, and they actually drop the whole mass down here. We do this again. This is for the main core optics that are hanging, the heavy guns. But essentially every other system where all the readouts are have the same thing, it's just laid out differently. And it's not quite as good, in fact. It's almost as good. And it works up from the ground, and we sit optics on it. They aren't just hanging. But we sit them upwards and then have pendulum again. And this is just because even the auxiliary system still can couple in noise if you work through how all that runs around the system. And that's sort of what that looks like. Here's some people crawling around in it to work on it. It's hard. You have to keep it really clean because it's in this really good vacuum. There's not much space. It's kind of fun. I didn't go in, but I got to work on a little bit out there. And of course, all of these active systems and all of the electronics to control them, there's all of these degrees of freedom, mechanical systems. You have to control all of that. So we have this big control system and this huge user interface and a team that is monitoring that everything is isolating well, nothing is shorting out and causing extra noise in the interferometer, and it all comes down to this control room. And you can just see that there's a lot to monitor. And some of that is optical beams, a lot of it's seismic isolation. Is there a truck driving up to the instrument that's about to rock the ground really badly? And so where does this lead the instrument? Well, the initial LIGO is the green. And actually, so these little peaks here that you see, those are the fibers. Those are the glass fibers vibrating due to thermal noise. And they're really narrow because the glass fibers are so high quality, very low loss. So it makes very single frequency, perfect violin strings. And so this is where we're at here. And these are the 2 detectors for the 01 run that made this awesome binary and spiral detection. But the design is actually about a factor of 3 better. And what's great is that this lets you see 3 times further. And when you think through 3 times further, 3 cubed the volume. So the rate that I quoted earlier could go up by a factor of hopefully 27 if we can fully achieve this, which, nothing's preventing us so far, we think. So that's like 1 a day. That'll be amazing. You can do some very good astronomy. And Ben, I hope, covers what all you can do with that in terms of what that means for the universe to see so many things and characterize them in your calculations. What I'm working on myself is future upgrades, how to make this even better. Because you get this awesome cubing of the volume, even small improvements really improve your rate and allow you to do more science. And so how do you take the design and make it even lower noise and more sensitivity? And this is maybe a too technical slide, I admit, but this is what I'm doing at MIT, is we're working on this photon noise, this hiss of the photons that you hear. Well, that's sort of a quantum mechanical effect. That's due to the fact that photons we're using as waves for our readout, but the noise is causing from the fact that they're individual particles. And the lab at MIT is determining ways of, and testing ways, which actually most of the technology has worked in isolation. We're now combining them so that we can install things that modify the quantum properties of this light so that we reduce the noise, so that the light behaves a little less like individual photons and more like, well, I don't know, more like waves, but it makes the photons arrive at more regular rates, so it's less of a hiss and it's a little quieter, and this will improve our sensitivity. This is a cool picture. There's a special method for doing this where you win in many ways. And so what does all this mean? Well, LIGO sort of sees in this range here, the gravitational waves extend down. There's other experiments that you can learn about online, and other systems that cause gravitational waves. This is just to get you excited about the whole field of gravitational wave science and all the different kinds of systems that you can look at. And they're all frequency dependent. So LIGO, being on Earth, can only really do these higher frequencies, where it can ignore low frequency rumbles of air masses moving and cars driving and seismic noise. And the lower frequency stuff requires other techniques, space, looking at stellar objects, looking at early universe. And I have to thank the whole collaboration, as I mentioned at the beginning. It was a huge team effort to make this picture. And all this technology is from them, not me. I'm hoping to have my piece in it as well. So, thank you.
Could you say something about the quantum noise and speed of that?
Yes. Yeah, it is a little hand wavy. So essentially, the way we think about it there is that when you have light, all the light is at some frequency, right? I mean, somewhere there's this photon picture, but it's all at some frequency. Like you have some carrier, like a radio transmits radio like waves out into space, and you pick it up on your little device. And the audio that you're trying to listening to is other waveforms on top of this overall thing that's being sent out for you to receive. And what's happening for the LIGO instrument is that it has some light wave, which is kind of nominal going in the instrument. And when you see a gravitational wave pass through, it causes distortions on that. And that's what you're really reading out, are the distortions of that original waveform. And the noise occurs as a sort of permanent distortion that's always being impressed on that original wave. And it's due to the fluctuations in the light. Like the light can't define itself well enough to not just constantly be rumbling around. And it's a quantum distortion. And that rumbling, you can interpret as individual photons arriving. And when you work out the math, it looks either way. It looks like individual photons arriving, or just a permanent kind of hiss or noise that you're going to pick up at every frequency. What we do with the systems that we're developing at MIT is we're manipulating those frequencies, and we're sort of combining those rumbling frequencies using external devices so that when they recombine at your detector, they look less like a rumble. This is still a hand-wavy answer, I admit. But, and it's called squeezing, right? So what we do is, I don't want to take up all the question time on just this, but when you do this combination, this overall rumble causes a sort of error bar. It causes, you have some coherent field that you're measuring here. This is the nominal field, and you're trying to see the waveform that's passing through as kind of a deviation that's kind of circulating around this, right? That's what's happening as the waveform passes through. Your power readout is trying to measure where this is here. The waveform passes through, and you see this thing deviate like this. But the quantum noise is a fundamental, the hiss is a fundamental error bar or uncertainty in your ability to resolve where that coherent field was. And the squeezing thing that you've, I guess, heard about is that when we manipulate the light and we put it through the interferometer, is that this error bar actually gets distorted. And what we do is we distort it in the opposite way from where we're measuring it. So the error bar is squeezed inward in one of the quadrants, and it must, due to the uncertainty principle, expand in the other one. But then when we try and read the signal causing this deviation, we can read it better because the error bar, this, what it ends up being a statistical error that the data analysis people have to deal with, actually shrinks. And that when I go through, that's a large portion of, this is bottom here, the shrinking of this error bar, this limit, this well at the bottom, is fundamentally the photon noise. And the shrinking of this error bar pushes it down. And that's what we're doing with the squeezing.
Could you post the website for the video that you showed at the beginning?
Absolutely, absolutely.
Just put it up here.
Actually, I apologize. I actually do have some handouts that I forgot to put out for people that I can give out. They don't have those exact websites, but I can post those up. I apologize for not putting those out earlier. And yeah, there's so many questions. You had your hand up.
Yeah. Has any effort been made, or has any detection been made, achieved, as to the origination point of this LIGO phenomenon in the cosmos?
So I think, yeah, I don't believe that there's been any follow-up that has specifically been able to pinpoint its source. I'm not fully up to date on everything that all of the optical people are doing. It's a very hard problem because we only have 2 detectors currently. And to triangulate from a 3D location with 2 detectors only gives you a localization that is kind of a circle. Now, when you look on plots, if you see them online, it's not a full circle. It's narrower than that, and that's due to some instrumental effects. But essentially, the size on the sky that we think that event could have originated from is like mini moons in size. And if you think of how sensitive a telescope is, how much further it looks than the moon, trying to find an object at that huge distance over such like many moons worth of area, for this event, it's not looking good that we'll be able to pinpoint it. But when we turn back on and hopefully see more events, they might be able to find those. That's actually a huge piece of science that we're hoping for. Yes?
As waves go, would you characterize a gravitational wave as a compression wave?
So this is, it's a little bit of a complicated question because, let's see. So a compression, I would say no, just to answer your question. So sound waves are compression waves, and they don't really have a direction. Like, there's no polarization of sound waves. Yes, go ahead. And in fact, yeah, I don't know if it's feasible. Yeah, if you want to. Thank you. Sound waves don't have any kind of polarization. Light waves have a polarization. They're not compression waves. And gravitational waves have a polarization. But it's, in some sense, a little different than light waves. Gravitational waves are sort of the next system up from light waves in that they both stretch in one direction and squeeze in another. And what we call that's a quadrupole wave. And they are fundamentally that in the way that they are described mathematically. So no, they're absolutely not a compressional wave. They're this other kind of wave that has a polarization, but it's a different kind of polarization than, say, light has. In that it stretches in one direction and squeezes in another. Yes? Yes?
What is the actual physical way that you introduce test signals into the system with blind injection?
Right. There's many ways you could think of doing this. So in one description of the gravitational wave and its effect on the mass, you can say that instead of saying the space-time is squeezing and stretching, you could say that the gravitational wave is causing a force on the mass, because as the wave passes through, the mass is in free fall. Just like we're in free fall towards the Earth, gravity causes a kind of acceleration as you want to fall inwards for the wave. So you can just say a 40 kilogram mass and the gravitational wave, that causes a force on the mass. So can we cause a force on the mass in a way that would look just like a gravitational wave? And in fact, the way it's done for LIGO is called the Photon Calibrator. They have a separate laser that they shine and they push in a waveform of some kind that they want to test and calibrate onto the mass. And the momentum of the light reflecting off causes a force. And the amount of light that they shine on it has like a NIST standard calibration on it. So it's calibrated like better than 1%. And so you can calibrate the force that you're affecting the mass with actually very well. And that's how the calibrator works. There's other ways to do it too, but that's kind of the most direct. And it's the way that it's done. Yes?
In multiverse theory, someplace I read the way we detect other brains is with gravity. Will the advanced design be that sensitive?
So, well, I don't know too much about those theories. Just know my light, mostly. But one of the things is that the gravitational waves emitted here, they're all these huge scales, right? Until we actually make the detection and we see a very small motion. Like they're really far away, the systems are quite big. And one of the things about most of these kind of brain theories is that the extra dimensions that you're talking about, they're actually really small. And so you need different kinds of experiments that detect those small scales fundamentally than this one, which is except until the final detection looking at systems of very large scale. So I would say no, it's not going to be sensitive in that way. Yes?
Are the electronics cooled to reduce thermal noise from the detector?
The electronics, yes. So not in this experiment. And actually the Cogra experiment they actually probably won't cool the electronics. So we actually, when do you need to cool electronics? You need to cool electronics when your signal is fundamentally colder than room temperature in some sense. Like cosmic microwave background experiments have to do this. But we gain a lot of our amplification just from our laser and our light. Like the fundamental physical system that we're running is like really our fundamental amplifier, not the electronics. And so we don't have to do any kind of clever cooling of the electronics to overcome the sensor noise in that way.
Yeah, the mirrors, they're
Yes.
coated with some metal, I assume.
Yeah, I'm not sure that I could tell you the exact compound, and it's actually like layers of compounds, but yes.
Is it? Okay. You don't know the thickness then?
No, each layer is only a few atoms thick.
Okay.
The layers themselves make little cavities that are tuned where the layer thicknesses are just right to be a reflector.
And how about the substrate itself?
The substrate is fused silica. It's glass, essentially, really pure glass.
So that's the ultra-low expansion glass then, probably.
Actually, I think the mirrors probably aren't that. The expansion of the mirrors, I don't think they tuned for that, so it's probably not. That's not like they aren't special in any thermal expansion way. I'm not sure actually, so maybe I should look. Yes.
Yeah, I'm interested. You're going to have the professor answer that question that some gentleman had with the expanding universe effect on
Dark energy.
whatever it was. Could you rephrase that?
Someday we will use gravitational waves to study dark energy. But not yet.
You need to see a lot further than even 1 gigaparsec.
You could do the sources of this distance, but you just need more sources and higher signal to noise.
Yeah,
Better
so
distances
maybe very advanced detectors that can see a lot of these things. So I guess to characterize this, you need populations of sources. And one source so far isn't a population.
The problem is we know too much about cosmology already for this to be much help yet, but we will.
Right, and so this plot is really cool because, in the hopefully not too distant future when we have space-based detectors like LISA, which he's very crazy about, then you can see much bigger systems much further away, and that can start talking about this.
Well, my question was going to be, was the frequency of your laser, was that critical? Did you arrive at that?
That's a great question. And one of the things that I'll point out is that you would think that if you chose a higher frequency laser, you'd be more sensitive, because I said that each photon is its wavelength divided by 2 pi. And what we really had to choose is, in order to do this and have a very stable experiment, you need a very stable laser. So really the driving factor for the wavelength that we chose is the technology, is that this 1064 laser, neodymium and YAG lasers, they're the best ones that you can buy for highly stable, reliable lasers. And if we went up in frequency, you could in principle gain some sensitivity, but all the technology, there's a ton of technology designed around this one wavelength, like the coatings, the mirror substrates, all of that stuff, the photodiodes. So it's really that this technology is kind of uniquely great. This wavelength is uniquely great for the technology. And you wouldn't actually gain that much because of the way you count the photons. You only actually gain is the square root of the frequency, or 1 over the frequency, just to go through the math. But yeah, it's not a critical factor, and it's driven by the technology. Yes?
At the source of these collapsing black holes, what was LIGO detecting before and after the heartbeat?
Yes.
That you've illustrated on the video.
That's a great question. So this is a system, in many ways we didn't expect to see because the black holes are so heavy, and the populations that are predicted before this event by astronomers didn't really expect there to be such heavy black holes. And why this matters is that these heavy black holes make lower frequency waves because they're so heavy and their merger happens at a particular time. Basically, if you had a lighter system, it would be a higher frequency. The reason why this matters, going back, is that since it started out such a low frequency, the waveform, while they were further apart before this final merger event, was too low a frequency to for us to be sensitive. We, like at the frequency where they were mostly rotating around, we could only see seismic noise. Our suspensions weren't isolating well enough at those frequencies. And then, so we only saw this final merger because that was the only time when they got close enough to be high enough frequency for them to hit our band and then for us to see it. When we hopefully see other kinds of objects like in-spiraling neutron stars, which are much lighter systems, and their merger occurs at a much higher frequency, we'll hopefully, when they're further apart, that too will be at a high enough frequency where we will have sensitivity. So we'll see them for longer before that event. In this case, we didn't, though.
How long was it before, after you started the system until you saw the first event?
I wasn't around at that time, so I don't know. I don't know that I can give you a number. Order of a few months. Yeah. Yes.
Is the gravitational wave stronger if we are seeing the system edge on, or when we're seeing both of them rotating around each other and they're the same distance from us?
So, right, when they are both the same distance, so that the plane of the in-spiraling system, like we're looking at the plane, not the edge of the plane. That is when we were most sensitive. And the reason goes back to like the kind of wave it is. It's this quadrupole wave. So when it's plane on, so it's two heavy masses. When it's plane on like this, it's two masses, big plus charges, okay? So I'll draw the plane here, okay, and they're spiraling in. So if you subtract the mean mass of the system, what this looks like is sort of a virtual mean mass and two subtracted masses here. And that's four things, and it makes the quadrupole wave. So when you subtract off the mean mass of this system, and it's rotating, it looks like plus minus. And that makes this quadrupole wave that gets to us. And when you look side on, you can sort of only see the two mass piece of it. And that doesn't generate gravitational waves, so that doesn't transmit. Does that answer your question? It's a little, yeah. It's essentially just the way the binary system is emitting outward. Yeah, it has to be stretching and squeezing, and when they're side on, it doesn't, like when they're side on, what's creating the squeezing in the other direction? Like when they're side on and you're just looking at the plane, Well, the wave can be stretching here, but when it's stretching here, it needs to be squeezing here. But there's no mass to cause this squeezy piece, if that makes any sense. It's a little, hopefully that answers it in a hand wavy way.
So every cartoon shows the waves propagating out from the plane, like the pictures, they show the waves.
Yeah, and I think that's just because it's too hard to depict. Otherwise, this 3D system, yeah.
I see.
So I just want to verify I understood you. Not only was this the fact that these were big enough black holes to have the right frequency, it's that they were also not in the right orientation of rotation to us, that the gravity wave came out in our direction?
That it's not? Well, it was enough for us to see it.
But it was also the plane of rotation that affected us, our ability to see it as well.
So it would have, I think, in our ability to do this parameter estimation, this is actually what BIM does, is a lot of the parameter estimation. And so when you look at it and you try and say, where is it on the sky and what was the plane of its emission, all of these different parameters of the system are kind of tied together because all you get is this one final waveform. And all of those different parameters affect how that waveform would look to your detectors. And so when you say, well, what was the system? Well, you have uncertainty. If you have uncertainty in one of the parameters, you kind of have a bit of uncertainty in all of them because they're all tied together in the way they'll show up. So essentially, I can't tell you what the exact plane was that we saw, the gravitational wave. And if I assume it was in one plane, then I might be able to tell you better where it was in the sky. But we don't have quite enough information to tie them all down. And when we have more instruments, if you tie down any one of those parameters better, it actually helps you everywhere in some sense. So more instruments will help us in a critical way. Because what's crazy is that if you can locate it on the sky better, you can actually locate what plane it was in better because of the way all the parameters are tied together in this way. And you should ask Ben these questions because I think he can probably explain really how they're tied together. Yes?
Yeah, one of the things. So you got neutron stars, then the other end, a little further on, you got black holes. Well, some astronomers and physicists think there might be quark stars, not quite black holes, but denser than neutron stars. If there was such a thing, would you detect gravity waves up to two of them?
I believe so, yeah. So you just need two massive objects where the mass is really concentrated. And the reason why the concentrated mass is important is that let's say you had two just really big plain stars, like stars have, you know, let's say one solar mass, but even bigger. But the problem with stars in spiraling is that they don't concentrate their mass enough to ever be close enough to have this really fast orbit. So like by the time they would be close enough to have this fast orbit, they'd sort of just be kind of one star. They'd have run into each other. Whereas these condensed objects or compact binaries, like neutron stars, maybe exotic things like quark stars, and black holes, they're actually condensed enough where there's free space between the two objects at the separation where they are rotating really fast and emit a lot of gravitational waves. Any other questions? I guess we're